So good morning, everyone. Bonjour à toutes et à tous. I'm very happy to welcome you all today to our first edition discussing the interconnection between arts and physics. I am Linda Michi, Deputy Attaché for the Office of Science and Technology at the French Embassy in the US, based in Houston, Texas. And we will have the pleasure to listen to two representatives and one representative of physics and two representatives of arts. From both the countries, France and the USA. They will be introduced by our moderator, Valerie Higgins, an archivist and historian at the Fermilab, the particle accelerator located next to Chicago. But first, let's hear a few introductory words from our General Counsel in Houston, Mrs. Valerie Barragan.
Good morning, everybody. I'm very pleased to be with you today. My name is Valerie Barragan, and I'm the Consul General of France in Houston. When I was asked to introduce this session, what came to my mind immediately is the etymology of physics. Physics comes from the Greek word physis, which means nature. Since antiquity and the philosophers of these old times, mankind made a commitment to the most exciting adventure, understanding nature, from the infinitely small to the infinitely large. Starting in the 5th century before Christus, Greek philosophers Democritus and Epicurus began their work on atomism. Pythagoras, Plato, Aristotle, and the Stoics studied the cosmos, the harmony of the spheres. This great human adventure never ceased to expand throughout the centuries, bringing together, beyond philosophers, artists and scientists who gradually specialized in their own fields of study. Understanding nature is at the heart of humanities. It's a powerful driver. Whatever the medium, paintings or equations, music or mathematics, the dialogue between artists and scientists engaged together in this common endeavor cemented the most beautiful periods of European history. For example, the Renaissance, thanks to the iconic Leonardo da Vinci, painter, but also engineer, botanist, anatomist, sculptor, writer, urban planner. Also the 18th century, with the Encyclopedia, edited by Diderot and D'Alembert, one outstanding collection of arts and sciences. This magnificent history is still alive. The largest research centers in particle physics, such as CERN in Switzerland and Fermilab in the United States, host artists in residency programs. Artists from various specialties in the fields of textiles, visual arts, paintings, music, come from all over the world to interact with physicists, to learn about their research, to visit state-of-the-art detectors and colliders for a few months, and then create artwork based on their knowledge and sensitivities. France has a great tradition of artistic and intellectual residency programs abroad. First in Rome in 1666 with Villa Médicis, then in Spain with Casa Velázquez, which opened in 1929, and Villa Kujoyama in Kyoto, which has been hosting artists since 1992. This year, we are inaugurating the 4th program in the United States, Villa Albertine. Here in Texas, Oklahoma, and Arkansas, Villa Albertine in Houston is more than ever and more than anywhere else a residence for artists and scientists. This year, its core topic is the renewal of imagination at the time of the space program relaunch. As a matter of fact, Villa Albertine in Houston is fostering the dialogue between artists and scientists. Cognitive processes are intertwined. Imagination stimulates knowledge, and knowledge stimulates imagination. Today, the General Consulate of France in Houston is pleased to host a discussion between a French-American particle physicist, an American textile artist, a French filmmaker, a discussion moderated by an archivist and historian. Like Leonardo da Vinci, both Italian and French, crossing boundaries both in knowledge and across countries, our guests are based in France, Europe, and the United States, between Houston and Chicago. Houston is an international city, a place of science and culture. The General Consulate of France in Houston is proud to promote an international and interdisciplinary event. The discussion is addressed to an expert audience, but also and above all to an audience that shows curiosity. I thank our guest for agreeing to participate in this event, which I hope is the first of a long series of meetings between artists and scientists. I congratulate the teams of the cultural and of the scientific services in Houston who organized this event. And to our audience watching online, to all of you, have a great time. Thank you. Bye-bye.
Thank you, everyone, for listening to this first introduction. And I will now give the floor to Valerie Higgins. As I mentioned, she's an archivist and historian at Fermilab, who will begin with a short introduction.
Okay, so welcome and thank you so much for being here, everyone. I'm Valerie Higgins, lab archivist and historian at Fermi National Accelerator Laboratory, or Fermilab as it's usually called, the United States' premier particle physics and accelerator laboratory. Bertolt Brecht, a German writer and playwright, wrote, "Even though humanity has often and for a long time had to do without knowledge and art, the fact remains that both are essential for us to be human. There is no one who is totally indifferent to knowledge, and there is no one who is totally indifferent to art. Art and physics are much more intertwined than commonly thought. Art can interpret and communicate scientific knowledge, and scientific breakthroughs require creativity. Art is all about organized perception, and physics interprets the visible world and the invisible world beyond the senses. Both artists and physicists explore the unknown and shape it with their visionary and revolutionary perceptions." I'm excited to moderate this event because at Fermilab, art and physics have always been deeply intertwined. For many years, the lab has hosted an art gallery and a performing arts series, and a few years ago, the lab established an artist in residence program. When Fermilab began operating in 1967, it was under the leadership of director Robert Wilson. Wilson was not only a skilled physicist and administrator, but also a sculptor who had a keen aesthetic sensibility and saw profound connections between physics and art. He frequently drew comparisons between building cathedrals and building particle accelerators. The 11th employee he hired for the lab was an artist who designed the lab's logo and color scheme, and for more than 30 years created striking artwork for the lab's publications and posters. The Fermilab site is also home to several sculptures by Wilson and architecturally unique buildings, which Wilson often had a hand in designing. On multiple occasions, Wilson wrote that it was important that Fermilab's physical and cultural environment reflect the beauty and profundity of the physics research performed there. Wilson's philosophy still permeates the culture of Fermilab. He laid out much of his thinking about connections between art and physics in a 1978 essay titled "The Humanness of Physics," and I can think of no better introduction to this event than to share some of his words from that essay. Near the beginning of a section on the aesthetic aspects of physics, he writes, "For a physicist, the laws of physics themselves have great beauty. The laws express so much in such elegant form that we can compare them to poetry. It is no accident that the laws of physics are beautiful. In groping toward many of the great truths of physics, intuition is an important guide, and beauty is one of the beacons which guide that intuition." Wilson goes on to describe how physicists like Einstein, Dirac, and Schrödinger were guided in part by aesthetic intuition. In describing his own experience designing particle accelerators, Wilson writes, "In experimental physics too, aesthetics plays a role. I, as an accelerator builder, have found great satisfaction in relating to the men who built cathedrals in the 13th century. I'm sure that both the designers of the cathedrals and the designers of nuclear accelerators proceeded almost entirely on educated intuition, guided largely by aesthetic considerations. My own experience has been in designing modern accelerators. These are exceedingly complex machines. To understand each complicated component and its relationship to the whole would go well beyond my own technical knowledge. So how do I go about designing? Well, I find out a little here by a simple calculation and a little there by a string of such calculations about the most important technical components. I then sketch those parts of the design on paper. After that, I just freely and intuitively draw in neatly appearing smooth lines, lines which cover my ignorance of detail. I keep drawing until the accelerator takes form and appears that it might work. Mostly I know it might work because it looks and feels right. It is when the parts and forms have essentially the same relationship that the parts of a sculpture should have to the whole that I am satisfied by the design. Of course, building, even designing a large accelerator is a complex team activity, just as it was with the cathedral. But if the conceptual design is aesthetically right, then one can depend on the members of a team to appreciate and respect that aesthetic form in their own creative contributions. What I am trying to express by a certain amount of exaggeration is that most of the effort of design is intuitive, that aesthetics are indeed a valuable and necessary guide in any design process, that these very human qualities are an important part of physics. Later in the essay, Wilson further highlights the deep connection between art and science. Physics is not developed by mechanically following an arbitrary set of rules that lead automatically to new knowledge. Not too much is known about how the mind of a physicist comes to produce new physics, just as not much is known about how the mind of an artist comes to produce new works of art. One thing is clear, there is much in common between what the creative artist does and what the scientist does. Scientists and artists even use similar words in describing their creative moments. They both usually pass through a morose period when their contemplation is deep and mostly at a subconscious level. Finally, what they do create just comes bubbling up from the subconscious to the conscious mind. Inevitably, this inspirational act is accompanied by a period of euphoria, an ecstasy which has been documented time and again for scientists and artists alike. Those qualities that we identify with humanness are as active and important in physical research as they are in painting or poetry. When we look at the relationship between art and physics, as Wilson did, it is not at all surprising that some artists seek inspiration in scientific laboratories as much as physicists do. The physicists and artists you will hear today will take you to a wide range of facilities, from CERN, the European Organization for Nuclear Research in Switzerland, to Fermilab in the United States, to a thermo-solar power plant in Spain. I hope today's program with physicist Christophe Royon and artists Lindsay Olson and Mathilde Lavenne will spark your own imaginations and open new doors for you between the arts and physics. Please submit your questions to the Q&A at any time, and we will ask some of them in the question and answer period at the end of the program. Our first speaker is Christophe Royon. He is a French-American particle physicist at the University of Kansas, where he is a Foundation Distinguished Professor in the Department of Physics and Astronomy. He received startup money to put together a team of researchers to work on discovering the Hadron, a new type of particle. The same year, Christophe was the recipient of the Humboldt Prize for his pioneering work. In 2019, Royon earned a grant from NASA to design and build a particle telescope to launch into orbit aboard a satellite. Please welcome Christophe Royon.
Thank you very much for this nice introduction. So let me share the screen. So, where is it? Here it is. So can you see my screen? And can you hear me?
Yes.
Okay, very good. Good. So first of all, I would like to thank, the people from the scientific group at the French consulate and also the French embassy, for organizing this event. I think it's a very good idea to make people talk together between physicists and artists. So I hope it will be just the first one of a long series. It's a perfect idea that should be developed more. So what I will do, first of all, is to introduce a bit the Tevatron and the Large Hadron Collider. I will try to discuss what is a proton, and then discuss, I will get some surprise, some strange event at the LHC. I will not tell you more, but you will see in the slides. So what I would like to stress, as it was mentioned before, in fact, we can say that science and art are closer than people might thought. When you think about art and science, you may think, okay, it's quite different. But in fact, there are two things which relate things and art from my point of view. First of all, the beauty of the instrument that you are using. It's a kind of a cathedral of modern days, as you will see in a few minutes. And also the way that we see the world. I mean, when you want to develop new models in science, you have your given vision, your new vision of the world, and you try to put it in equations, as if an artist has his own vision of the world and try to put it in a painting or in films or wherever you want to put it from the art point of view. So there is this kind of new view of the world that you want to express in a new way. So I just show you here a kind of a drawing that I have at home, actually, which from Diego Rivera. You see, so these two people are working hard, I mean, in the fields, and we are doing the same. We are trying to dig more the universe to understand the best way possible the universe and the way it was built. So in the next slide, let me discuss very briefly why we are building accelerators. I mean, probably you know, I mean, since already the antiquity, I mean, people have been looking to as small thing as possible. So you start with some microscope, I mean, which were designed very long time ago. And you can see, let's say, some micron kind of scale that you can see with a microscope. Then more recently, there were electronic microscopes that were developed that allow you to look for instance, the DNA, and the size is about nanometers. And then if you want to see much smaller objects, like for instance, nuclei, or even smaller, see them between quotes like quark and gluons, you need particle accelerators. So particle accelerators, you can see them like a microscope of modern time, where you can see really tiny objects. And this is what is put here. You see that basically you get for quarks about 100 million billion per inch. So it's a really extremely small kind of object. So, and we have a long history in high energy physics or particle physics. First of all, I mean also, and this is the Greek term of atom means something that you cannot cut. So this was at the time of the antiquity. I mean, the Greek people defined atom as the elementary structure that exists. And then you see that we had to wait quite a long time, I mean, to find that it was not an elementary object, but it's made of nucleus and electron. You see that it was discovered only in the 1910 or 1940s for the electron. And then people noticed that the nucleus was made itself of proton and neutron, and this was again in the 40s. And then only in the 70s, so only 50 years ago, people discovered that these objects were also made of quarks. So for now, there is no evidence that there is a substructure for the electron and the quarks. That's why there is question mark now for the LHC, but we didn't find so far any substructure for this object. So these are today the fundamental particles that exist. So what the tools do we have? I mean, we have two kinds of colliders. It was mentioned before. So the first one, which is in the US, close to Chicago, Fermilab, where we collided, in fact, I'm talking in the past because the Tevatron is closed now, we collided protons and antiprotons. And something that can be also quite astonishing, I mean, for most of the people, is that we produce indeed some antimatter. So we produce antiproton and we collide them with protons. There were two main experiments that were called the CDF and D0. You have the view of the ring here, the Tevatron ring. And I was member of the D0 collaboration. Then today, so the biggest experiment we have in the world, the biggest collider in the world is located at CERN, which is on the border between France and Switzerland. And it is a proton collider. So this is the highest energetic collider in the world, so 13 TeV. And just to give you a feeling, I mean, I give you the circumference, about 27 kilometers. It sits underground. It's about 50 to 100 meters underground. The energy per beam is ordered 800 megajoule. Just to give you some idea, 1 megajoule melts about 2 kilograms of copper. And the power consumption is of the order of 120 megawatt, which is the power consumption for a medium-sized city. For instance, I mean, same scale as Ann Arbor. So just to give you some feeling of the size that you are talking about. It's a huge object to collide protons and to understand what matter is made of. So what are the components? When you have a machine, you want to build the accelerator, what do you need? Obviously, you need to accelerate the particles. I mean, as fast as you can, because if you accelerate them, you can understand what is the structure of that particle. For this, we use the cavities that are shown here on the photos on the right. And then to bend, because we have a circular machine, so we need to bend the beam. And for this, we use magnets, so dipole magnets. You see a photo of the tunnel from CERN, and quadrupole magnet. And this quadrupole, even if it was installed at CERN, you see that it was built by Fermilab. So it's always a world collaboration that appears for this huge machine. When I am talking at CERN, you should not think that it's only French and Swiss people that are working here. People are coming from all over the world and collaborate from all over the world just to do physics and to understand what matter is. So why do we want to do the LHC? You may wonder, I mean, why building such a huge machine, which is that expensive? I mean, why do you want to do this? And in fact, what we want to do is to reproduce the conditions that are as close as possible at the time of the Big Bang. Just to give you some idea, so this is the age of the universe. You see, we stand here today at about 14 billion years, for instance. And with the LHC, the energy that is accumulated at the LHC, we reproduce the conditions that were about 10 to minus 30 seconds after the Big Bang. So really, a tiny fraction of time just after the Big Bang. So this is basically what we can study at the Large Hadron Collider. That's why we can hope to produce some new particles that were produced at the time of the Big Bang. So what do we have concerning the machine? So in that way, you can say, okay, it's extremely energetic. I mean, because as I told you, we are very close to the condition to the Big Bang. And in fact, in terms of temperature, when two protons collide at the LHC, they reach a temperature which is 10 to 17 degrees. So maybe it doesn't tell you much. I mean, such a huge number. I mean, the 10 be like this and the 17. But just for comparison, the temperature in the sun, which is probably, I mean, if we were asked what is the hottest place in the universe, you would have told me in stars for sure. I mean, like the sun. So 10 to 7 degrees. So there is 10 orders of magnitude in temperature between what we do at the LHC and what we have on the sun. So it's really impressive. And again, as I said, it creates conditions that are similar to 10 to minus 13 seconds after the Big Bang. So you could say, in a way, this is probably the hottest spot today in the universe. So what we created, what humanity created, of course, locally, I mean, a very small scale, is some conditions that is probably the hottest spot in the universe. So then you wonder at the same time, and it's a bit funny if you want to think about it, it's also the coldest spot in the universe. Because in order to use the magnets at the LHC, we are using superconducting magnets, and the temperature is very, very cold. We are talking about minus 271 Celsius degree, or in Fahrenheit is minus 457. So you can imagine that this is probably the largest fridge that we have also on the planet, because you saw the size, about 27 kilometers. And to cool it down, I mean, it's not like your fridge at home, it takes about 1 month and about 10,000 tons of liquid nitrogen and 100 tons of liquid helium to cool it and to keep it cold also all the time while we are doing collisions. So also, as you may guess, it's one of the largest instruments of Earth. The idea of a detector is quite simple. You have basically these two protons that collide. In most of the cases, they are destroyed, and you want to take a photo of what went on when they collided. So we are doing the same that you do with your electronic camera, except that we have a huge camera because the detector is about 50 meters with 100 million electronic readout channel. So it's similar basically to a digital camera with 100 megapixels that takes 40 million pictures per second, because we have 40 million collisions per second. So we can take this kind of event and record this interaction using also computers. And also, in addition to the camera, they are sensitive to light, but also other kind of radiation. So there are two general experiments that are called ATLAS and CMS, or two big experiments, and there are two other ones which are smaller, LHCb analysis. And also I wanted to give you a scale of this kind of experiment. So probably you have already been to Mount Rushmore, the photo on the left. And you see the CMS detector, which is on the left, and the ATLAS detector, which is on the right. So this gives you the kind of size, I mean, of this detector with respect also to the trees that you see also on the photo. So these are huge detectors to detect tiny particles. And it's also very heavy. If we compare the weight of the CMS detector with the Eiffel Tower, in fact, CMS is about 30% heavier than the Eiffel Tower. So we have a huge apparatus. What is the idea of a detector? I will not enter into detail, I mean, obviously, but the idea is always the same. you need different layers in a detector in order to stop the different particles that are produced in a proton-proton collision. Without entering into the detail, there are some particles that we call photon and electron, probably you heard about it. They don't need that much matter to be stopped. So these are the first particles that we see. Then we have proton neutrons. They didn't, usually a bit more matter, like a steel, to be stopped. So we have all this kind of steel-based detector to stop this particle. And finally, we have another series of particles, maybe you heard about it, muons. And these muons need a lot of matter to be detected and to be stopped in the detector. That's why the biggest part of the detector that you see usually is the muon detector. And I should mention also one particle that you know probably, the neutrino. The neutrino, it can even cross the Earth without interacting for most of them. So you can imagine, of course, that we cannot stop him in our detector. So the way we see it is by we see some missing energy inside our detector because the neutrino disappears from our detector. So now let's discuss a bit what is a proton. If I was asking you, in the street, what is a proton? Maybe some people who have told me, who heard about it, it's made of 3 quarks, 2 up quark and 1 down quark. You see them, this blue one, the red one, and the green one. Okay, very good. So it's maybe the vision that you have of a proton, but for me, I have a different vision, which is much more complicated. And this is the bottom plot that you see here. You still see my 2 up quark and my down quark, but you see a very strange object. There are these kind of strings that we call gluons, which are inside the proton. And also there are some spheres, like these purple spheres and the green spheres, that correspond to quark-antiquark pair. So you see that this vision of the UUD structure of the proton is not the real one that we have in physics and is much more complicated object. And why is it relevant? When you do proton-proton interaction, so it is illustrated with these 2 protons that collide, and you see they are made of gluons, quark, and so on. And what interacts is, in fact, the object inside the proton. So the quark gluons inside the proton themselves. And what we do, we cannot decide, we have no control what process actually takes place when we do the interaction, but we just measure, and then we have to find out which quark or which gluon interact inside the proton, so which collision indeed happened. So probably you heard about the standard model of particle physics. So and this is also the beauty, in a way, of particle physics, in a way that people introduce what we call symmetries in order to understand the structure of matter. And they find that we have 6 quarks, which are shown here, 6 leptons that are here, and the 4s that are here for electroweak, also electromagnetism, and also gravity. So it's always the same. I would say that in art, you impose some symmetry, some kind of order in the world in order to define your model. In the same way that art will try to give your vision that you have of the world. And this is the same in particle physics. We have this vision and we try to see how it can describe the universe. So I want to discuss now some very strange objects, that happen, and we see them every day at the Large Hadron Collider. I think it will surprise you. And these events, in fact, we have 2 protons that collide, and after they collide, they are intact after the interaction. So they collide, they produce some new particle, and still they are intact. So I always give an everyday analogy. It's as if you have one collision between 2 big trucks that happen, and after the collision, my 2 trucks are intact, basically, and plus you produce some small cars. So it's exactly what you see every day at the LHC, which is very surprising. So we can use this kind of events, in fact, to look for beyond standard model, what we call beyond standard model physics, which is related like to extra dimension in the universe, or also dark matter that can be produced using this kind of events. But they are very striking by themselves. And we see them, again, we measure them every day at the Large Hadron Collider. I just want to finish by mentioning, a recent discovery since it happened this year. And this is related to this kind of events, what we call elastic scattering. And what we observed is exactly what happens when you are playing pool. Probably all of you played already pool. You send a ball against another one, and the balls are scattered at different angles. The balls are not destroyed usually when you play pool, but they are intact. So this is exactly the same. That's what happens between proton-proton or proton-antiproton collision. So, and what we noticed, this figures is the only really figure of what was published, very recently in Physics Review Letters, that show the difference if you count the number of events between proton-proton and proton-antiproton interaction. Proton-proton interactions, they are the red triangles, and proton-antiproton interaction coming from Fermilab are the blue circles. And indeed, you see some difference between the number of events that are predicted. You see it yourself between the blue circles and the red triangle. And this was explained by the discovery of a new object that was discovered recently, which is called the Hadron, and she is built to an odd number of gluons. I introduced the gluons, so it's a bit technical, but 3 gluons, 5 gluons, 7 gluons, and so on and so forth, that was never observed until today. So this was basically, I would say, I wanted to show it to you because this was the new result of this year that made the headlines of the press and also communication from CERN at Fermilab. So I just want to show you this cartoon because I think it's a bit funny, but the way we are doing as physicists, I mean, as you see, there are these people, they are in Africa, probably looking for some animals, and they don't even see the lion, which is just sitting behind them. So this is the way that we need to do in physics, is to look everywhere. I mean, you don't know what you will observe. You can be guided by some models and everything that gives you some mind, the way you see the universe. But at the end, when you do the experiment, we never know. Maybe something that we'll observe will be different from what you are thinking. It's how you make progress. When you get difference between what you are thinking and the measurement that you do, you understand better the universe. So it's always the way that we are thinking about the universe. So I just finished by saying, I mean, I discussed the Tevatron, which is proton-antiproton collider, and the LHC, which is the highest energy collider in the world for proton-proton. It led to many discoveries. You heard probably about this Higgs boson discovery that happened a few years ago, and this year the Hadron, and again could bring many more unexpected results. So I didn't have to mention it, but in addition to doing physics, there are also many applications that we are building because we need to be at the edge of science concerning detector development, concerning electronics. So there are some developments that can happen in medicine, imaging, or cancer treatment, or also, that as was mentioned at the beginning, we have collaboration with NASA, for instance, to measure cosmic rays. So by all this collaboration, it's how we can make progress in the different fields of physics, not only in high energy physics. And as I said, there is beauty in physics and detectors, which is related to art. And you have, I mean, some photos of some object that I put in the bottom that are at home, at least for me, some African mask, or you see some Indian, also what they call a storyteller statue and a bear statue on the right. So thank you very much.
Well, thank you so much, Christophe, for that really fascinating talk. So as a reminder, we will have a question and answer session at the end of the event. You can submit your questions for any of the speakers at any time in the Q&A or in the chat. So our next speaker is Lindsay Olson. Lindsay's artistic practice grows out of an intense curiosity about the ways our society is supported by science and technology. She has worked as Fermi National Accelerator Laboratory's first artist in residence with the CMS experiment at CERN, the Field Museum, the Center for Acoustics Research and Education, and many other labs. Lindsay uses her art to help connect people to both science and art by booking exhibitions, speaking widely, and publishing articles about her projects. Please welcome Lindsay Olson.
Hi, everyone. It's a pleasure to be with you here today. I just need permission to be able to share my screen so I can get my slides up. It's a pleasure to make new friends too, which is always a wonderful experience when we're putting together a program like this. I'll just wait for just a second till I get control. There we go. Okay, as Valerie mentioned, I'm an artist, and the basis of my studio practice is science, and it takes me out of the studio to places like this, a cavernous ring of equipment designed to accelerate tiny bits of matter at near the speed of light. And here at Fermilab, scientists want to crack open the secrets of neutrinos, and I want to explain it through art. Now, for many people, science seems like an insurmountable subject, and one of those people includes me. But all this changed when I realized I could use my training as an artist to learn scientific concepts. For years, I had been painting idealized views of the Chicago area waterways, but I had been editing out the built environment, and all of this changed on a canoe trip down the Calcite Channel near Chicago. My husband and I canoed past an engineered waterfall, and it was in such an obscure location, and somebody had taken a great deal of time and trouble to engineer this waterfall. The process of finding out who built the structure and why led me to the world's largest wastewater treatment plant in Stickney, Illinois. And once there, I suddenly realized that I could use my training as an artist, and I could learn enough engineering that would tell the real story of water in a dense urban area. So I know this is going to sound pretty weird, but I actually fell in love with science in the middle of that very wastewater treatment plant. Now, it would have sounded a lot more glamorous if I were to say that I fell in love with science in the accelerator ring at Fermilab. But that work, that body of work led me to Fermilab's art gallery and its curator, Georgia Schwender. So after she attended an opening of mine, she invited me out to Fermilab for a tour. During the tour, she turned to me in the middle of it and said that she had wanted to establish an artist residency for a long time. And she invited me to be the first artist in residence. So both of us, I think, had goosebumps at the moment. It was just a very exciting moment. And my first thought when she mentioned this was to say, wow, someone is actually inviting me to do the work that I love. But my second thought gave me pause. I thought, geez, this is a pretty complex subject. This would be a real test of my ability to use my training as an artist to learn science. So before I could talk myself out of the offer, I accepted it. And as Valerie mentioned earlier, the founding director at Fermilab, Dr. Wilson, was himself both an artist and a scientist. And so he integrated that into all parts of the lab. And one of the wonderful parts about working with Fermilab was that there were so many people who were willing to graciously share their time and their expertise with me during the residency. Now, Christophe showed this picture of the standard model. And early in the project, someone at Fermilab handed me this book by Dr. Don Lincoln, who is a senior scientist at Fermilab. So I took this book with me on vacation and puzzled over the first chapter for a long time, which is all about the standard model. Now, eventually Don became my science advisor and generously spent a lot of time teaching me about high energy physics. But in the beginning, I really struggled with this material. Now, most of us are familiar with the periodic chart of elements. All the elements are organized by atomic weights. But the standard model is to physics what the periodic chart is to chemistry, but instead of dealing with atoms, the standard model expresses life in the subatomic realm. The model describes life inside protons and neutrons. And so this is what it looks like to those of us without mathematical training, and this is what it looks like to people in science. They will recognize this as the Lagrange equation. So one of the biggest obstacles to learning about high energy physics or life on the subatomic realm was accepting how particles behave in the quantum realm. It's counterintuitive to the ways in which we perceive reality. Life in the quantum realm is so weird that you don't need illegal substances to blow your mind. Now, I struggled with this material till I figured out I had to make space for both versions of reality. The reality that I experienced through my senses on a daily basis, and the reality that physicists have discovered on the quantum scale. And one example among many of this dual view of reality is that things that appear solid to us are in fact made up of fields of wiggling, jiggling particles, to quote Richard Feynman. He's one of my favorite physicists. Many artists use oil paint, watercolor, and other traditional material, but to create my artwork, I want to figure out a way to have the least amount of distance between the viewer and the art. And everyone uses textiles in their daily lives, so creating work from them felt like a natural choice. Now, as Christophe mentioned earlier, the study of physics is actually ancient, really ancient. So I wanted to use colors that would suggest antiquities. And I included a democratic use of high-end textiles like silk and lace with workaday fabrics like denim and canvas. And of course, I had to choose blackboard paint to put in these pieces because they're ubiquitous at the lab. Now, I also use a lot of time-consuming processes. Have we missed all my slides? I just had a screen.
No, we've been seeing the slides.
Okay, so I'm going to start here from the current slide. Can you see my current slide now?
Yes.
Okay.
Yes, yes.
This, it's funny, Christophe, that you should mention a history of particles, because that's what this piece is about. This piece is about a sort of royal road to discovery, and it starts with the electron and it ends with the Higgs boson. Now, historically, hand embroidery and beading were used on luxury clothing. So using these sorts of processes to create the art elevates the subject matter. There's a little bit closer look at some of the beading on this piece. The standard model of particle physics has been hugely successful in predicting particles, including the Higgs boson, whose existence was experimentally confirmed in 2012. However, after years of correctly predicting particles, physicists know that the standard model doesn't tell the complete story. In this piece, you can see in the very center right here where my cursor is traveling, that is a shortened version of the standard model, and it looks provisionally attached to the piece. I'm expressing the idea here that the standard model may have to be substantially changed as new theories are developed. And in the very center of this circle here, I've left room for undiscovered particles. So my work, like current theories, might prove to be obsolete in the future, and I'm trying to stave that off. So after working on these pieces for a while, I brought the artwork in to show my scientific advisor, Don Lincoln, and he looked over the pieces and kind of like, oh, that's kind of nice. And I pointed out all the particles. And then I said to him, look for the Higgs particle. And so he was looking and looking and looking. And I finally had to point out the tiny H's that I had embroidered into the background of all the pieces that relate to the standard model. The Higgs particle was predicted for about 50 years before it was experimentally confirmed. And I wanted the artwork to reflect how hard it was to discover that particle. So suddenly Don was really into the artwork, and he was really happy about that. During the residency, I was also invited to join a group of scientists and artists working together at CERN as part of the Art at CMS group. Now, as Christophe mentioned, also the Large Hadron Collider is a humongous machine. It's the largest machine ever built by humans, and it houses 4 experiments. So on my first day, when I arrived at CERN, the Art at CMS program held an exhibition at the P5 site. And I set up my artwork, but I also had a chance to see what other artists had set up and created for this project as well. Now, Christophe gave you a really great size indicator for this piece of equipment. This is the compact Muon solenoid. This is the CMS experiment at CERN. And if you look at the very bottom of your screen, you can see these teeny tiny little humans. This detector and all the detectors at CERN, there's nothing that is custom. All of these big giant machines have to be custom made. There's nothing out of the box for them. So this CMS detector weighs, as Christophe mentioned, a lot. It's like 14,000 tons. There's 4,000 people from around the world who collaborate on this experiment. And it's just amazing. Everything boggles your mind at CERN, how big everything is. So inside the Large Hadron Collider, there's 2 beams of protons that are traveling at near the speed of light. And they're traveling in opposite directions. And what happens is eventually the operators align the beams and they crash, all the particles crash into each other. And they make these big, messy collisions. And out of those collisions come the information that scientists are learning about how particles behave. When I traveled to Geneva, Switzerland, I also had the opportunity to visit a book exhibition at the Martin Bodmer Library. They had a spectacular exhibition of medieval manuscripts. These ancient texts were the inspiration for a group of pieces I created related to this research at CERN from the CMS detector. In the studio, I created a kind of collision myself between medieval illuminated manuscripts and this experiments. Now, medieval illuminated manuscripts were used to transmit the most important information of their day. And I wanted to create a modern day illuminated manuscript that would help tell the story of the science being conducted at CERN. So off the bat, this piece may not look like a book, but if you look in the very center, there's a brad here, and it's holding a fan of skinny pages together. Now, maybe some of you have seen a paint chip book at the hardware store. That's the format I used. It mimics the shape of the detector nicely. Tucked inside each origami box in this artwork are questions that physicists would very much like to answer. Why do the forces have such disparate strengths and ranges? Why is there more matter than antimatter in the universe? And is there something smaller inside quarks and leptons? In these pieces, I'm also connecting the concept of the study of the tiniest bits of matter and saying that they're intimately connected with information about the Big Bang and the origin of the universe. So I've included images of dark matter mapping as well as references to particle collisions. Back at Fermilab, I still had more work to do for the residency and more science to learn. At Fermilab, scientists study another group of particles called neutrinos. Fermilab is the world leader in neutrino research. Our universe is permeated with neutrinos, and they are nearly massless, neutral particles that interact so rarely with other matter that trillions of them are passing through us each second. So in this piece, I've constructed a kind of curtain that suggests a theatrical space, and it's a way to present a collection of these mysterious particles. I've used subtle shades of silver, steel, and gold to represent the three flavors of neutrino particles. Scientists hope one day to discover why these particles oscillate. Neutrinos emanate from the Earth, from the sun, they arrive from the distant cosmos, and neutrinos are manufactured at Fermilab with sophisticated technology that begins with a small bottle of hydrogen. This piece portrays the billions of neutrinos in the beam as an elegant cascade of metallic fibers. And my scientific collaborator, Don Lincoln, estimated in his head, I might add, that I used about 3 miles of metallic embroidery floss for this piece and this piece. Now, in both pieces, I'm using the visual metaphor of nets to suggest how detectors capture images of these rarely interacting elusive particles. The art borrows techniques used in high fashion to project an image of dark glamour. Here, the detector is represented by velvet squares joined by lines of beads in 3 subtle shades. Again, I'm using the 3 colors of seed beads to express the dynamic nature of neutrinos. So I just want to take a moment to say that the accelerator at Fermilab is different than the one at CERN. The accelerator at CERN, as we mentioned before, has 2 beams of protons operating in opposite directions, and it crashes the particles together. But at Fermilab, the neutrinos are accelerated, or the particles are accelerated in the neutrino accelerator, and then shot at a distant target. So it's a slightly different kind of accelerator. I was interested in learning about high energy physics, but I was also curious about the actual experiments. And I was given permission to take rigorous radiation safety training in order to accompany the operators into the guts of the experiment. Now, this was a very privileged view. There's not too many people who get to go where I went inside the experiment. And I got to meet people like Cindy Joe, who at the time was an operator. She's since moved on to a different position. So accelerator science is all about riding a bucking bronco of particles. And because the particles in the beam all have the same charge, they want to spread out. So there's more than 1,000 superconducting magnets strategically placed around the ring that steer and compress it, and while they're traveling at near the speed of light. Then they're shot into a distant target. And sometimes, but rarely, neutrinos do collide with other particles, and scientists can use that information to study their behavior. Without this complex machinery, neutrinos interact so rarely that it would be almost impossible to study them in one person's lifetime. Now, I created a series of drawings that represent these powerful magnetic forces that are steering and controlling the neutrino beam. In order to create the large-scale drawings representing the ring in a triptych, this is only 2 of the 3 pieces, I used the stage of Wilson Hall to create a very large arc over 90 inches. You'll see this in a later shot in the talk. I've also used wet on wet ink here, which is difficult to control, to express the magnetic forces. I wanted these drawings to look slightly out of control. Someone at an opening asked me why I illustrated the particles as looking kind of sloppy over here. And it isn't that the particles are sloppy, it's just that it takes so much energy and so much engineering to control the particles because they're so positively charged. They don't travel in a tidy little line like some people might think. Controlling nature is not easy. So collecting inspiration for sustaining a creative life can be as diverse and as rich as imagination allows. Like many visual artists, I also collect hundreds of images that help me clarify ideas I'm developing. But the images alone are not enough to help sustain me through the long arc of a project. Collaborating in the right situation is exciting. It's almost exhilarating sometimes, and definitely mind expanding. But occasionally my energy flags, I get discouraged, and I feel overwhelmed. And it's at times like these that I'm looking for heroes who have trod a difficult path and that can inspire me to get back on track. Dr. Ray Davis is one of my favorite heroic scientists. The fusion reactions in the sun generate abundant neutrino particles and send them spinning out through space. In 1961, Dr. Davis designed an experiment to capture these elusive particles, but his experiment yielded some very odd results. Davis was only able to account for 1/3 the number of theorized particles in his detector. And for years, he had to contend with colleagues who thought that his math was off or that the design of his experiment was flawed. And in the 1970s, with refinements in detectors, it was discovered that neutrinos oscillate between flavors as they travel through space. And in 2002, Ray Davis's meticulous work was honored by a Nobel Prize. The treasures housed in museums are also a rich place to mine for visual inspiration. And I was lucky enough to have the chance to go to the Art Institute to see the work of Swiss embroidery artist Lizzie Funk. The textile staff were kind enough to roll out her monumental embroideries. Now, most embroidery artists were quite small, but I'm showing you this to give you an idea of just how huge this work of art is. She had a gigantic vision. So Lizzie Funk created modernist embroideries that were every bit as exciting as the painters of her time. She scaled up her ideas and expanded her stitch vocabulary. I'm inspired by her boldness and her inventive ideas. I want to keep pushing the boundaries of stitching just the way she did. Her work remains fresh and unique today among embroiderers, and Lizzie Funk is a Picasso-like figure minus the ego and the drama. I'll share a link with you towards the end of the talk where you can see more of her work. To be successful, my projects need a few key ingredients. First, the artwork must be grounded on a solid scientific foundation. I interview scientists and other staff, I tour the experiments, I take training, and I read deeply. I design my projects as a full immersion experience. And out of this scaffolding, I create accessible art that helps explain scientific concepts. This struggle to understand a particular corner of science is a powerful creative catalyst. Second, I employ all my training as an artist to make accessible, impactful art. Images can touch people in places where words cannot, and I only have a few brief seconds to snag the attention of the viewer. It's also important that the artwork stands on its own, so even if someone is not interested in the science, they can enjoy the art. The last ingredient is passion. There's strict rules defining what activities qualify as scientific research, but before an experiment begins and after it's completed, there's plenty of room for emotional connection. My goal is to lure in science-phobic people with handsome art and surprise them with cool science. The Fermilab residency and the CMS experiment were extraordinary opportunities to work with world-class scientists and professional staff members. As a result of the work of the residency, I've had dozens of opportunities to exhibit work, write articles, and speak about using fine art to connect people with high-energy physics. Both science and art are deep expressions of our humanity, and it's time to help spread the word about what scientists are learning about our universe. More and more artists, poets, novelists, playwrights, singers, and artists are helping to amplify the message that both art and science are a powerful and necessary expression of our humanity. And now I want everyone to know that you don't need a PhD to fall in love with physics. Thank you, and I'll stop sharing here.
Well, thank you, Lindsay, so much for that fantastic presentation and for sharing your beautiful artwork. It really brings back some great memories of getting to see your work in person at Fermilab. And for everyone in the audience, remember that you can submit your questions for Lindsay or any of the other presenters in the Q&A or the chat, and we'll ask them at the end. So our next speaker is Mathilde Lavenne. Mathilde lives and works in France. She is a visual artist and a filmmaker. After studying philosophy and Latin American cultures, Mathilde Lavenne focused on working with glass, ceramics, and drawing at the HERE, High School of Arts of the Rhine in Strasbourg, and her attention to the material evolved towards video art, cinema, digital art, and sound at the Frenois National Studio of Contemporary Arts. Her films have won awards at the Ann Arbor International Film Festival in the USA, the Ars Electronica Digital Art Festival in Linz, Austria, the Clermont-Ferrand Digital Art Festival in France, and the Francois Schneider Foundation in Wattwiller, France. Please welcome Mathilde Lavenne.
Hi. I turn my screen. I think it's okay.
Yes.
Valerie, thank you very much for your introduction. I'm really happy to be part of this wonderful event and this first edition. Thanks very much to all the incredible teams. I'm going to do this presentation about how physics collided with my artistic practice, with my Frenchy English. So sorry about that. Maybe I have first of all to confess that I was not an excellent student in physics, but I rediscovered it my own. And on the other hand, I have always been passionate about science fiction in literature or cinema. And recently I discovered the writings of Ursula Le Guin and Octavia Butler. So, to start again here, you can see my first collaboration in 2013 with a team of scientists from the CNRS on the question of human interacting with machine, AI interaction. After that, I joined the Frenois, which is a contemporary art school that puts young artists in contact with researchers, scientists, and theorists, all in an incredible professional conditions of cinema production, new technologies, and digital media. Among the themes that characterize my work, the ghost, hidden or unspoken stories, residencies of forms in the dark reveals the types of animism, beliefs, and magic of the territories I explore, from Norway, like here you can see, to Mexico, from Poland to Argentina. And I want to give the voice to the living people who inhabit them in a kind of synesthetic approach of the landscape, as in my first film, Focus on Infinity, that you can see here, or here in the installation called Artifact Digital Necrophony, as well as from ethnographic analysis, fieldwork, interviews, meetings with experts. The journey and the movement that it applies to the body and the gaze is the active principle, in a way, my methodological continuum. It relies on serendipity of encounters to act out the passage from my nebulous of research, literature, philosophy, history of science, and technology, to the final form of a film or an installation. Here you can see a picture of my movie called Tropics. I made this film in Mexico, in an area that had been colonized by the French in the 19th century. The technology used was a scanner, what we call a scanner, a 3D scanner, that allowed me to cross matter, time, and men, and reveals the ghosts of a kind of lost paradise. So maybe best is to share with you a picture of the movie, an extract here, short extract.
saber más sobre los orígenes de la familia. Y la genealogía es muy compleja, ¿sí? Porque más allá de los abuelos de nuestros bisabuelos o tatarabuelos, o sea, existieron más personas, pero pues ya no hay nombres. Los nombres que quedan conforme las generaciones van muriendo, pues hay datos y cuestiones que se van perdiendo. Pues que antes pues no existía la tecnología que hoy existe para comunicarnos, ¿no?
So back to the presentation. At the Ars Electronica Festival, I met on this occasion in Austria, the antimatter physicist Michael Dozer, whom I had already heard of in Mexico during my previous residency. And these links lead to a series of exchanges about his fascinating work about antimatter. And and I made a short visit to his laboratory at CERN, the antimatter factory. I also I was not able to see the Large Collider, this wonderful cathedral, as Valerie said, but it was a really interesting to see this laboratory of research. And that same year, I was received at the French Academy in Madrid, the Casa de Velázquez, for a film project about a solar thermal power plant in the south of Andalusia. And this film centered on this temple of solar energy, was inspired by the ancient alchemical illustrations of Robert Fludd, that I share with you some picture here, and also my exchanges with a sociologist specializing in ecofeminism called Benedict Zitouni. When I met Michael Dozer, I had the intuition that he was a kind of contemporary alchemist. So I wanted to ask him for the formula of transmutation and the elixir of youth. His words completely enlighten the pictures of my movie called Solar Echoes, that I want to show you a little extract now.
Le prix à payer pour pouvoir comprendre la nature, c'est de la rendre séparée de nous, de la considérer comme un objet à part ce que nous sommes nous-mêmes. Et donc d'une certaine manière, c'est ce qu'a fait la science. Chez les alchimistes, une grande partie de l'approche a souvent été de dire que c'est une recherche de pureté en eux-mêmes, de tentative de se mettre dans le bon état d'esprit pour que cette expérience de chimie, d'alchimie fonctionne. un cas, on a une vision de la nature qui est inhumaine, où l'être humain ne joue aucun rôle. Dans l'autre cas, on a une vision de la nature qui est complètement en connexion avec notre intérieur, avec nos états d'esprit intérieur. Et donc d'une certaine manière, la pierre philosophale, la recherche de la matière première, est une sorte de réflexion de leur propre pureté interne, de leur propre individuation. Je peux transmuter du plomb en or.
So back to the slides, I really hope you enjoyed this short extract of the movie. Here you can see some pictures showing an experiment with electron blasted into a cloud chamber that inspired me for the modelization 3D of the solar explosions. I have to tell you that during my residency in Madrid, I met Silvia Texera from the Fermilab in Madrid, and we made a little cloud chamber, do-it-yourself cloud chamber, but we finally chose to use those wonderful inspiration images. During the shooting and the residency, I also wanted to transform solar radiation into sound, and I started a collaboration with the astrophysicist Xavier Berthoud, who had collaborated with the artist Thomas Saraceno at the Palais de Tokyo in Paris. So just before the pandemic, we worked together with the observatory data around astrophysical phenomena linked at that time to the CERN, the cosmic radiation captured by the Pierre Auger Observatory in Argentina. Then I was granted a residency at the Cité Internationale des Arts in Paris, where I was able to research in the archive of the Marie Curie Museum with the historian of science, Nathalie Pijard-Migaud, doctor in the history of science, mainly of on the history of women in science and medicine. There I found the trail of Marietta Blau, particle physicist, who she didn't discover, but she discovered a way to fix in photography the plaque with our partner Herta van Bacher, the disintegration of the trail of disintegration stars, which are tracks of massive nuclear disintegrations. And what drew my attention was that she was a female scientist and Jewish, and she had to exile to Mexico with the help of Albert Einstein, and then to the United States during the Second World War. And for her work, Marietta was nominated several times for the Nobel Prize in Physics, but was never recognized for her discoveries, joining the long list of invisible women of the history of science. So with this new project called Dark Stars, I am starting a reflection on the place of women and minorities in science and their invisibility as developed by Margaret Rossiter theory entitled Matilda effects. Here you can see some example. Among these women, I chose, three portraits caught my attention and allowed me to bring out the strong points that I seek to explore, inspired by their commitment, their lives, and their work. So the invisibility of women in science, the astrophysics, astronomy, and social minority, and also the ecology and research in physics. This project is in his first research step this year, thanks to the University Paris-Saclay, societies that create link between the scientific laboratories of research in Saclay and the artists. So I'm really convinced that something, a vision can be shared, maybe to finish this project around women scientists and their work. I really want to connect it to current research in physics and also astrophysics in order to awaken imaginations, and I hope it will bring me to create new narratives. Thank you very much.
Well, thank you so much for that fantastic presentation and for sharing those wonderful clips. I really want to see the full films now. So we'll now begin the question and answer portion of the event. So remember, you can submit your questions for any of the panelists in the Q&A or the chat. And I'd also encourage you to take a look at the chat, because people have been posting some interesting comments and sharing some interesting resources in addition to their questions. So first of all, we have a question for Christophe, and that question is, how do most physicists see similarity between art and physics in the randomness between particles, objects, or when high order is achieved?
So it's not an easy question, I must say, to answer, because I can answer it, I mean, from my point of view that I was telling, that for me, there is some natural relation, let's say, between art and science in the way that the people want to express the relation with the outside world. I mean, like with the universe, for instance. So this is the way I feel it myself, that so in science, you try to understand the universe from first principles using mathematical rules. And with art, you try to understand with your own eyes the universe, with the human eyes, of course, which means, I mean, and this is also related, to quantum physics, if you want, that this is the way you see the universe, which is a kind of personal way. It's modified by the fact that we observe the universe as human beings, and we see only partially the universe as we feel it. For instance, I mean, it has to be visible. This is what we see for our own eyes for most of the people. So this is the way we feel it, and we represent the universe. So the way I would answer it. I mean, I cannot say, of course, on behalf of all the physicists, because I mean, probably other physicists would have some ideas, other opinions, but this is the way that I would put the link myself. And another link, as I said, is also the beauty of the objects that are built. Like you saw, I mean, some photos of the detector, the CMS detector or the Atlas detector. And I would say it's like today's cathedral. I mean, when you build these gigantic instruments, which are used to measure tiny particles, when you think about it, I mean, you use this huge instrument to make the smallest particles that are produced on Earth. This is a kind of paradigm, I mean, also between the two. And at the end, it's a beautiful object. I mean, multiple color and so on. So even the way that some photos, as it was shown also at the discussion by the artist, photos of this object were done, it looks very nice by itself. So this would be a bit my answer. Again, maybe not everybody would agree with me, but this would be my own answer.
I think that's great. Then our next question is for Mathilde. They asked, in what area of Mexico did you film Tropics?
Okay, I film, thank you for this question. I filmed Tropics in Veracruz, in the north of Veracruz, in San Rafael, which was also a short colony, French colony, colonized by French farmers in the 19th.
Okay, and we have another question that it's not directed to anyone in particular, so I think anyone can take it who would like to. Which other scientific domains have inspired artists?
Oh, I can take that one.
Yeah, please go ahead.
I can take that one if you like. I've worked with a number of different scientific research projects and in a number of different ways. And so I mentioned the wastewater treatment plant, which is really, really unusual. I don't think I've ever heard of another artist working with wastewater treatment. But I also had the chance to go to sea for 3 weeks working with ocean acousticians. And that was fascinating because for the first time I was actually able to participate in the science. And mind you, science has some very dull moments, just like art has some very dull moments. You know, water sampling is not the most exciting thing. It's kind of like pipetting. It's very repetitive. But, you know, it was wonderful to be a part of the science crew and to be a contributing member of the team. So that was really interesting. But I think there's room for art and science connections everywhere. You just have to search your own passion and see where it leads you.
Yeah, I agree. I mean, I think really it can be to any domain of science. I mean, it doesn't need to be high energy physics or nuclear physics. I mean, it can be really solid state physics. I mean, any domain, and even outside physics, it could be biology. It can be completely, any domain of science can be related to art. I mean, the way you see it. So, and also, as was mentioned, I mean, the same problem that you have something like art when you want to do a painting or you want to do a new film and so on, it takes time. And sometimes there is some frustration, I mean, to find new ideas and so on. And in science, it's a bit the same. I mean, it's not every day that you will make a discovery. You should not imagine a scientist with doing calculation and finding something every day. I mean, it can take years and years and years and years. Like, I mean, people say, for instance, Einstein was saying, I got only one good idea in my life. I mean, this is what Einstein was saying. So you have to represent that you try many, many times, you make progress little by little. And even if you get a negative result in the sense that you didn't find what you thought, it's not completely negative because you made progress. You know that this way of thinking is not the correct one. You have to go somewhere else. So this is how you make progress in a way.
So our next question, I believe this is geared mostly towards Christophe, but I think anyone else could also weigh in on it. What are some of the similarities and differences between what physicists see as aesthetically beautiful in our theory's equations and the aesthetic reactions that an artist might want to evoke in their work?
Yes, so it's also not an easy question, actually, because it's also something which is a bit different between an artist and a physicist. Like, I mean, it's probably for somebody who is not a physicist, I would guess an equation seems something a bit abstract. I mean, they don't know what it means, don't know what it represents. Like, I mean, you showed this big page of equation that represent the standard model. I think if you show it to anybody in the street, people will be puzzled and say, okay, I don't see anything beautiful in it. So, I mean, for this, I think you have to know what is behind this kind of equation, that it can be part of ruling the world in a way. This is the equation that will describe how the particles interact together. So you have to know this kind of scientific aspect to be probably sensitive to this kind of equation. And an artist who maybe doesn't have any knowledge in this structure can be sensitive to other things. I mean, just the beauty to say that to think that, for instance, everybody is made on the same quarks, the same leptons, the same gluons. I mean, if we are talking about all the individuals which are attending this meeting, or even the table now, I mean, we are made of the same basic object. So this is something fundamental, and probably an artist can be sensitive to this. An artist can be sensitive also to the beauty of the detector, or as it was shown in the two talks that we had, I mean, today, which are and very nice, the artist talk. So there may be different sensitivity, but it's complementary. It's not the exclusive. So both of them are possible. And the same way, myself, I'm also sensitive to the beauty of the detectors and everything. I mean, even being a physicist, one doesn't prevent the other. This is maybe the way I would answer it.
I just want to add something to what Christophe has said, and that is that as an artist, it is tremendously inspiring to sort of ride the enthusiasm that scientists have for their research. I mean, as everybody's enthusiastic about their own corner of the universe, but when you collide two people who are enthusiastic about art and somebody enthusiastic about science, it's like this wonderful synergy that can really carry you along.
Yeah. So we have a question for the two artists. The question is, were any of the artists initially frightened of quantum mechanics?
Mathilde, do you want to go first?
I don't know. I'm frightened.
Yeah, it was really intimidating. I mean, you think about walking into a place like Fermilab, which is like the world's leader in neutrino research, you know, one of the biggest, most important physicist labs in, you know, the United States, and it was really intimidating. I was working with a lot of people who were absolutely brilliant. Nearly everyone there has a PhD. So it was also very humbling, but it was also very exciting, and it really helped me change the way I look at reality and look at the way my art can intersect with science. It was very inspiring, but yeah, it was nerve-wracking.
Yeah, I can say that for my really modest experience, yes, I was not frightened. I was fascinated, and maybe the meeting with Michael Dozer, the scientist, helped me because of actually, yes, the enthusiasm, the energy, and the imagination that well, it brings me to a lot of intuition, visions, and imagination because of the meetings, because of this sharing area. Yeah.
So we have another question. How have the art and artists influenced physicists and other scientists? And this might be something anyone could answer, or also Christophe, if you have any artists or any works of art that have influenced you as a physicist, that might be interesting to share.
I mean, myself, I mean, I like art. I'm interested in many different kinds of arts. I mean, like I put some photos of some object I have at home, I mean, as example. And especially recently, I was very much interested in African art, for instance, also. I mean, they have different way maybe to see the world, which is not that far away from the Indian art also in the US, actually. You see some similarities. So this gives you maybe some ideas how you see the world. And this can give you also some ideas how you see the world from a scientific point of view. Because as I said, usually I mean, the way you can build a model, you are guided obviously by science, scientific facts. I mean, that's completely obvious. But you have also some models in the way you see the world. And you try to see if the way you see the world can be put mathematically, and does it agree or not with the experimental result? Because if it doesn't agree, okay, then your vision of the world is completely wrong. You have to change, you have to adapt it. So there is, so this kind of personal way you see the world, or some artists can see the world, can also influence maybe the model that we can, with which we can describe the world maybe. This is the way that I would think in a general way. So it can be some guidance. I mean, an example is quantum mechanics. As you know, it's not very natural from everybody's life. What we predict at the quantum mechanic level, at the particle level, the behavior would look very strange at the particle level. Like I gave one example for these diffractive events when we collide protons, and both of them are intact after the collision. I mean, you don't see this in when car collides in everyday life. I mean, so you see this kind of special behavior that are at the particle level, and you have to understand it. So artists can maybe have their vision of this kind of new world, which is not common to our common life, let's say.
I'd also like to say that as an artist, our job is to look carefully. But in addition to looking, I feel like my job as an artist is to empathize with not only the people, but the corner of science that I'm working in. And when I create this work based on someone else's research, it's a way to reflect their life's work back to them, which is why I often feel a tremendous sense of responsibility to make sure I get the message right and that I've accurately represented this person's work. And it's kind of, it's a wonderful way to connect when you show someone artwork that's about their life's work. It's an instantaneous, I understand your work. You know, it's a way of building an emotional connection. And I've found that to be very, very powerful.
Well, we have another question, someone for the artists. How much did you know about quantum mechanics before you started engaging with these subjects for your art? And I'll expand on that a little and add to that. And once you did engage with quantum mechanics or related fields for your art, did that change your relationship to those fields or your relationship to physics or how you approached it?
Well, I got through my entire scholastic career totally avoiding science and math as much as possible. So I come to science with a very fresh perspective and a sort of courageous ignorance.
And for me, on the other hand, I've always been interested, in art, what it is modern art or ancient art. This is really, I've always been motivated to understand also how and why people created art. As well in Europe or the US, which is more Occidental style, or also in Asia or in Africa, where you can get different kind of style and how people were inspired as a function of time, which I think is very interesting and related also to probably the structure of the human brains. Because you see some similarities according to the place where you come from, which I think is very interesting. So something which can be profoundly human, let's say. Yeah.
Well, I think we're getting towards the end here, so I'll ask one last question and anyone can take it, or everyone. What unique opportunities do you think interactions between art and physics present for engaging with non-scientists?
I think for me, it's important that we keep the interaction and the dialogue with people. Some people who are neither nor scientists nor artists, and we have this kind of meeting where people can attend, can ask questions, can also hopefully soon see the exhibition directly. Live and not only by Zoom when the situation with COVID will be better. I think this kind of interaction is very important between the people, and also that people can, I say everyday people can learn what science can bring to them. So, they like some applications, what is the fundamental research, what do we learn about the world we live in from the science point of view, and also maybe from the artistic point of view. That is a way also complementary, and it's not against each other by far. So I think from this point of view, it's a nice and natural development. And I would like really to thank you for organizing this, which I think is a good idea. So.
Yeah, I think it's important to have this connection between art and science, because the art allows us to meet people where they are with science. Because science can seem very esoteric. Even among physicists, there's corners of physics that don't speak to each other because the language is so different. The focus of the research is so different. But by using art, it's like a way to kind of bypass some of the barriers that people might feel, the intimidation that some people might feel about approaching a subject like scientific research, and it just makes it more accessible.
Yeah, I would like to add that it's a really big not responsibility, but it's really important to start to see maybe differently and to engage different vision and to move also science, and it's really important to show people those researches in laboratories. Even if I think that art is not an advertising of science, that's why I think that meeting scientists or make scientists meet artists, it's really, really fundamental to share the vision and to be able then to transmit or to share with people. But I'm not. I'm an artist, but I don't have either the power, for example, to give a message to people. Myself, I discovered that we were every time we had particles crossing our body every time last year. So And I thought, but it's not possible. And also, Michael explained to me what we know, and as you did also, Christophe, what we say about the Big Bang right now. And I think it's impossible that all people didn't know that it's our history, it's our world. So yeah, that I wanted to add.
Yeah. Well, thank you so much to all our presenters for your really wonderful presentations and for your thoughtful discussion during this question and answer session. And thank you to our audience for being here and for all of your great questions. So I'll hand it back to Linda now to conclude the event.
Thank you, Valerie. Thank you, Christophe. And thank you, Mathilde, and especially Lindsay as well for this lively presentation today. And we want to thank you, our audience, as well, for attending our first presentation discussing how the arts and physics working together make visible the invisible world of high energy physics. We hope that this very first collaboration inspires future programming with a similar arts and science theme that also highlights the interdependence between our two respective countries. So this webinar has been recorded and will be shared with you as soon as possible, especially for those who weren't able to join us today. And today's attendee will be amongst the first to hear about our upcoming seminars related to this subject. So also, as mentioned initially by our General Counsel, the Villa Albertine Artist Residency is an exciting step for the French-American collaborations in diverse artistic fields, focusing among others on space, science, and climate change. So please don't hesitate to contact us if you have any question, if you want to give us your feedback, and to learn more about the general missions and programs that we lead at the cultural and scientific offices of the French Embassy. We would love to hear from you. And in the meantime, I hope you learned a lot, as much as I did, and we hope to see you again for future events. Have a good day all.